start with a few words about the history of this field. In the 16th years of last century, during the Cold War, Bob Altman, Nobel Prize, Michael Masher and Richard Stearns worked on the United States Agency of Disarmament and Arms Control, and they carried out some researches concerning the problems of gradual disarmament. It was a very great uncertainty about the arsenal of Soviet Union, and in these conditions they should develop some theories that allowed to deal with such situations. And this theory was rather general, covering questions of information concealment, revelations, signaling, and related ideas in very many situations of uncertainty. And such game theory models of repeated incomplete information have the following specific. First of all, the main key is repetition in such models. Repetition allows to exchange information between participants of such models. The other important feature is that each participant has to act at each period of interaction, but he will know the result only at the end of this interaction. Also, there is a private information in these models, in such kind of models. It may be private information about the future of processes or events, private information about the preferences of the opponents, or even about of his own preferences if they deal with some uncertainty. And the third very important specific is that participants may observe actions of their opponents, and using this observation they update their beliefs about processes and about some unknown events. And the principal difficulty of analysis of such situations is that when players or participants exploit their private information, they should take into account that they reveal this information to their opponents. So they should balance between taking advantage from the information and concealing it as long as possible. And what about financial markets? It's a very important application of this theory, originate in 2002. In fact, one of the fundamental problems in financial analysis is the problem of stock price dynamics. And traditional financial econometrics doesn't completely solve these problems because the main way to deal with such problems is to find the best dynamics that fits historical data. But it doesn't allow to say about the origin of such dynamics. And traditional explanation for the randomness of prices on financial markets is completely exogenous. And it was first formulated in a good way by Bushingia. This is a formulation. It means that there are uncountable number of very different events that influence the prices on financial markets. However, Demilier and his PhD student Moussa Saleh suggests that this explanation is not complete, and the part of the randomness of prices is endogenous. This randomness is introduced by market agents in order to maximize their profit. In fact, the situation is following. Institutional investors on stock markets traditionally have better access to the information about the prices on the risky assets. They have better skills to analysis the processes of information, or in some cases they even have inside information in a traditional notion of inside information, so they can be directors of the firms that are trading the shares. So such investors are big players on the market, and they have better information, and everybody on the market knows who are these people or organizations. It's very difficult to conceal these facts. Other not so big market agents absorb the moves or the actions of such big players, and they try to extract informational content of their action. So they try to update their own small parts of information, absorbing the activities of such big players. So, if such big players, insiders, inform agents act naively, and if they make moves that deterministically depend on the information, then they will completely reveal the information very quick, and they lose their informational advantage. It's not very good for such insiders. And the only way for them to take benefit from information without revealing it too fast is to introduce some noise on their actions or some randomness in the processes of exchange risky assets. And this idea was demonstrated in the basic paper of Demir and Saleh, with the model of interaction between two differently informed market makers. Here is the model. In this model, we have two types of players. It's insider and uninformed player, or we can say aggregated market of all uninformed players. It's not important in the model. Before exchange period starts, at the step 0, some chance move or some exogenous factor influence the prices of risky assets. This factor determines the price C with accordance with probability distribution E up to the finite horizon n, at the moment n. All players know the probability distribution period, probably some statistic expectations. But insider often receive a message that contains the true liquidation share price. Then at each step from 1 to n, both players simultaneously propose prices for a share. If player 1 posts a bigger price, then he buy one share from player 2 for this price. If player 2 proposes more than player 1, then player 2 is a buyer. If they propose equal prices, then no transaction occurs at this step. After each step, the bids of players are publicly announced, and players remember the history of it. But they can't calculate the benefit because they don't know the true liquidation price of the share. Player 1 knows, so he can, but an informed player can't. He can do it only at the moment n, after the moment n, the last moment of bidding. And the aim of each player in such situation is to maximize the final value of portfolio. We mean the money plus liquidation value of obtained shares. We also suggest that before bidding start, each player have enough money and share to interact Then models with real admissible bids are developed by Domier and his school, and the discrete models that are more realistic, they are developed in St. Petersburg Institute for Economics and Mathematics by Blavatsky and Krebs. The results for discrete models are the following. It was shown that if the biddings are very long, if they are unlimited duration, then insider's total gain is finite. The value of this game is the following. It means that the profit of insider is proportional to his uncertainty about the liquidation share price. It's a variance of liquidation share price. And it was also shown that insider's optimal strategy in this case generates the symmetric random walk of transaction costs with absorption. Here the absorption means the reading of true share value by an informed player. In this case, game terminates naturally when an informed player knows the true share value. Then insider naturally loses his informational advantage. More natural model is a model in which players may propose different bid and ask prices for the share at each step of interaction. And the exchange mechanism is the same, but bid-ask spread is fixed by commitment with the stock agency and equal to the value. In this case, we obtain the upper bound for insider's gain in the case of infinitely long interaction. It is also proportional to the variance of the share price, but we also can see that the spread make a great influence, and then in models with greater spread, insider's gain is small. But the interesting effect of this game is that price dynamics generated by insider's optimal strategy is more complicated than symmetric random walk of transactions cost. So we can't easily take that result and prolongate it to this case. The other interesting situation is the following. What happens if the exchange is limited in time? And what happens if inside information suddenly becomes common knowledge or suddenly reveals? For example, insider thinks that he is immortal, but something happens and he should stop this interaction, this trading. In this case, he is failed to win some part of his gain, and we will call this loss of insider's profit as a price of sudden disclosure of inside information. We also obtained exact formula. It's rather big for this value, and we show that this value has the order of magnitude less than alpha to the power of t. T is a moment when this disclosure occurs. Alpha is less than 1. It means that if the disclosure occurs later, then insider's loss is rather small. So it's not very. Insider shouldn't afraid such situation. And this observation also allows us to recommend insider to use this optimal strategy in the infinite stage game, in the trading of finite length t, because it's a rather close strategy to his optimal strategy. And once these results are published, and if you have any questions, I will try to ask them. Thank you for your attention.
Any questions?
Do you try to do you calculate optimal strategy in case of random stock? You show that if the random stock is inherent, not very, if probability of random stock is low, then infinite strategy is good. But what would happen if probability of random stock is high? How do it influence on the policy of the players?
In fact, this result works with any moment of stopping, random stopping or some determined exogenous stopping, because this moment is not known to players, to insider. That's why we can say that this strategy works even in the case of sudden moment of stopping.
If the uninformed player is not just a random investor, but has sophisticated methods of estimating the value of C might be, did it change the
in fact, I didn't tell you, but we also find the optimal strategy of uninformed player too, and it's very natural. So he should observe the actions of insider, and if insider posts too big prices, then uninformed player also increase his prices, and if insider posts very low prices, then he should decrease his prices, and this is optimal behavior. It's rather nature, and an informed player who can guess it rather easily. Such.